Hi, this is a video that will be a complement to the class Nonlinear Modeling of Reinforced Concrete taught by Dr. Gunner here at the University of Toledo. In this video, I will show how to model a simply supported beam using some features in SAP2000 to simulate nonlinear behavior of the elements such as shear hinges and moment hinges. And I will also go into details on some a little bit more specific advanced analysis features such as displacement base and force base and a few other topics. So this is the problem I'll be solving in this video. And this is basically a simple supported beam with a load in the middle. This is the beam configuration. This is the cross section. We have some material properties right here for the reinforcement, for the concrete, and these are the dimensions of the beams: the width, the height, the effective depth, the length, the span, and the reinforcement configuration. We have some questions here to answer, which I'll only come back at the end of this video after we model everything and got the results. But basically we have to estimate the following, which are the cracking load, the ultimate load, the midspan deflection at failure, and the crack pattern and failure mode. Alright, so I have my SAP2000 open here and I will start a new model. And for this, I'll use the grid only. And for the modeling part, since this is not actually the focus of this video, I will assume that you already have some knowledge on how to model a simple structure such as this simple beam. So I'll go through this very quickly and I'll probably won't show all the steps, so this video can be a little bit shorter. So I'm just gonna create this grid here. I'm gonna make the grid on the XZ direction because the Z is my gravity. So I have 3 and 2. My X spacing will be half of the beam, so 3660 divided by 2. Let's hit OK. Let's change the view to XZ. I'll create my concrete material, come in here. I'll modify this one. I'll say concrete beam. I won't bother going into the weight because I won't use the dead load of this beam. I'll just model the live load, which is the force we are applying. The modulus of elasticity, we're gonna use the one provided, so 36,000. We leave the Poisson, we leave the coefficient, the compressive strength 22.6 megapascal, and we'll hit OK. For the reinforcement, we will have to create one material for each of our longitudinal reinforcement. So we have 3 right here, M30, M25, and this top one here, although it's not shown in this picture, is the M10. So we will need to create a SAP2000 material for each one of them. Alright, so here I have all the materials that I'm gonna use for this problem. So now that we have all the materials, we still need to draw where our element's gonna be, but first let's create our cross section. So we're gonna go into frame section, add a new property, and for that I can't use the concrete because if I do use the concrete, it will give me no option to specify different reinforcements right here. So for that, I'm gonna go to the other and come into the section designer. I'll create this concrete section. The base material will be the concrete I just created, and right here I'll click on the section designer. So I'll start using these two. Click on the rectangle, right click on the center of the axis here, the origin of the axis, right click on it and specify the height and the width. Height 552, width 305, and let's hit OK. Let's click on this one to maximize. Let's right click, check that we have the material correct, and we have the height and the width. It's at the center. Okay, everything looks good. Let's create our reinforcement. So to create the reinforcement, I'm gonna use these two, the draw reinforcement shape, and I'm gonna use this line bar. What this will do is that it will allow me to draw a line, and it will put bars along this line. So in our problem, we have 2 layers on the bottom and 1 at the top, and we are gonna try to do the same right here. So now we're gonna edit these layers to look like the problem. So let's start editing the first rebar layer here. So first let's change the diameter to 30 which is the bottom bar. Let's change the bar spacing to 178, which is the spacing of the bar here. And let's put yes to end bars. So you see that we have more bars than we want. We only want 2. So now let's edit where this layer is. So we can see here x1 and y1, which is the location of this point here, and x2 and y2 is the location of that point. In terms of height, in terms of depth, we can calculate going back to our problem. It doesn't show on this figure, but the distance from the bottom to the center of this layer is 64. So we have 552 divided by 2 minus 64, which is 212. So going back to SAP, we can put the y1 and y2 to minus 212. Click OK just to check, and you see it goes down a little bit. Well, we want this point here to be where the left bar is and this point where the right bar is. From the problem, we see that the distance between the bars are 178, so that left us with 305 minus 178 divided by 2 for each side, which is about 64 millimeters as well. So distance horizontally and vertically is the same. So going back to SAP, here we can come and change the x1 and x2 points. So this will be minus 305 divided by 2 plus 64. That will be minus 88. The x2 will be the positive of this number. Hit OK. So our first layer is at the correct position. Alright, so the cross section is here. The reinforcement layers are already done. So one thing I forgot to do is to assign the materials to each layer. So right click on the reinforcement layer, come to the material section, and it shows up when you click it, so just cancel it and select the correct material that I just created before. So the bottom layer is 30 and hit OK again, and do the same for the other two. Alright, so now that we've finished the longitudinal reinforcement, we are going to go to this shear reinforcement, the stirrups. So unlike the longitudinal reinforcement, we won't explicitly model the stirrups here like bars, like the ones we are seeing here. To consider the influence of the shear reinforcement, we will include the confinement effects of the stirrups in the concrete material. So to do that, I'll right click here on the beam, on the concrete part, and I'll go to the concrete model and change the Mender unconfined to the Mender confined. And this window here opens where we can see a stress strain curve of the concrete. Here on the right side, SAP2000 asks for how many bars we have longitudinally on this beam. And you can see that there's only one diameter to input. So SAP2000 thinks that we will have a fixed diameter bar along this entire beam. So basically it thinks that we will have a column, which we normally have a uniformly distributed reinforcement throughout the entire cross section. That's understandable because confinement plays an important role when we have compressive members like columns, but it can also be important for beams, especially when we have a compressive controlled beam behavior such as concrete crushing. But for this part, we will try to balance out the rebar's diameters that we have here to kind of make SAP2000 do the correct calculation based on our reinforcement layout here. Our maximum diameter is 30 and our minimum is 10 I'm gonna put a 20 bar, and we can see that the longitudinal reinforcement does not play a very important role in the stress strain response diagram here. I'm gonna go back to, let's say, 5. I don't remember which one it was, but you can see that the curve doesn't change much when I change from 5 to 20 And the numbers of bars here, we have 3 and 4, 7. I'm just gonna leave it at 7. And again, you can see it doesn't change a lot. But this curve will change considerably when we include the shear reinforcement right here. So here in the confinement material, I'm gonna select my stirrup material that I created. And the bar size we have from our problem, a bar size of D5, which is 6.4 millimeter and 32.2 in area. So the bar size that gets closer to this that SAP2000 have here is number 2, which is 32.258, which is pretty close, so that's why I'm using here. The longitudinal space, as in our problem, 210 millimeters. So I'll put this 210. The numbers of ties in the height is 2 and the width is 2. So we have one bar coming here and one bar going down, so 2, and one bar on the bottom and one bar on the top, so 2 on the height as well. So in the height, we need to specify the distance between the center line of the bars that goes on the bottom and on the top. So we can calculate that easily from the cross section and from the distances right here. Alright, so now you can see a big difference in the stress strain response of the concrete here from our confinement layout. So let's click OK here again. So now we have defined our entire cross section. We have our concrete correct, our longitudinal reinforcement, and our confinement reinforcement all set up. One thing to notice here is that although the confinement reinforcement is basically the shear reinforcement, what we just did for the confinement layout won't affect in any way the shear calculation of this beam. In fact, SAP2000 won't even calculate the shear of this reinforced concrete beam, because it does not calculate reinforced concrete shear effects on its analysis. The only way to include the shear effects on this analysis is to put shear hinges on this beam. Stress strain response we just saw won't be used for the shear hinges as well, and I'll show you here on the SAP2000 analysis manual. I'm in chapter 6, material properties, at page 83, which talks about nonlinear material behavior. And here it says that the nonlinear stress strain curves are currently used in only 2 applications, which are described above. The first one is the fiber hinges, which we will use, and the second one is the layered shell element. We won't be using shell elements, so we won't actually bother about this one. But here in the fiber hinges, SAP2000 defined fiber hinges as the ones that are used for the couple axial force and biaxial bending behavior. So there's no shear. The shear hinges the SAP2000 implement is not considered fiber hinges. So the shear hinges we will implement won't consider anything we just created here. We will use the fiber hinges to capture the couple axial force and biaxial bending behavior of this beam later on. And for that hinge property, the nonlinear behavior of the concrete we just created here, this stress strain response will be accounted for. So let's click done, and now we can proceed to drawing the elements. So I'll use the draw frame cable. The section is the concrete section I created, and I'll draw 3 nodes. Close this, press S. So we have 2 nodes, which will be the supports, and the center load, which will be the force. Alright, so now that we have our supports, we can start to talk about the hinges that we will use in this beam. So the placement of the hinges is very important, and they should be located at the locations that their respective effects are critical. For example, a moment hinge should be placed close to where the moment in this beam will be maximum, and the same applies to the shear hinge. So based on the loading condition that we have in this problem, which is a point load in the middle, we know that our moment will also be maximum in the middle. And for the moment hinge, that's where we normally put our moment, exactly at the section where the moment is maximum. So our moment hinge will be located at the center of this beam. The shear hinge is a little bit different than the moment hinge in terms of its placement, and shear hinges should be placed. They're also critical location, but for shear there is a different concept of where is the critical location to its placement. For this problem, I will use definition of critical location that the ACI code uses, and I'll show you right now what it is. So here we are at the ACI code. I'm using the ACI 318.11. This is page 163, and we are at the clause 11.1.3. So here at this figure, we can see that it refers to the typical support conditions for locations, factor shear force V ultimate, shear ultimate. So here we can see that the critical shear is located at D away from the support, which is the same conditions that we have in our problem. We also have DOA here. For this case, when we have the tension loading on this element, the shear critical location becomes the face of the support, in contrast with DOA from the support. So this is where we will put our shear hinges in a SAP2000. So just to make a brief summary, we have the moment hinges at the center where the moment is maximum, and shear hinges D away from the support on each side. So in addition to the two shear hinges right here, I'll also put two shear hinges D away from the point load. And if you go back to the ACI code, we can think of our point load more or less as a column going into this beam, over which we have this critical shear location D away from where the point load is. And that's what I'm going to do in this beam as well. And you can also think of it in terms of shear diagram and moment diagram. So we know that the moment diagram is maximum in the middle, and the shear diagram is maximum from the support to the center, and in the center it changes side and it's constant up to the other support. So here at this section we will have both higher moments and higher shear. In contrast to this shear hinge, we will only have high shear and low moment. So those are the critical sections for the case we are doing in this problem. So you can put shear hinges and moment hinges in this entire beam if you want, but the ones I'm considering here are the critical ones, and they will probably govern this loading condition we have here. So to include the moment hinge first, which is the simplest, we're going to select the element we want, come to assign frame and hinges. We will put the auto hinge, and the relative distance will be 1, which means the end of this element we selected. So we will be at the center of our beam. So we're going to click add, and now it asks us to tell him what type of hinge this is. So we're going to select concrete beams in flexure. You can see that there's no shear, there's only flexure and axial. And here we will select if it's either moment 3 or moment 2, and everything should be okay. Hit OK here and click OK, and we will see our moment hinge at its right position. So if we come here to add our shear hinge, come to assign frame hinge. So if we come here and select the hinge we have, let's say we want to change this to a shear hinge. So we click on modify here, and we want to select the shear effect, but there's no shear hinges to select from the table. So because SAP2000 doesn't have the shear hinges to select right here, before we assign them to the beam, we will have to come to define section properties, hinge properties, add the new property for concrete, put it shear hinge, save it as a deformation controlled, and change the effect to shear V2. And here, this is where we're gonna put the information of our shear hinge. So in this window here is the only place where SAP2000 will consider shear effects in our frame element beam. For this video, we won't change anything in this window. We will leave everything as the default calculated by SAP2000. So before we hit OK and implement this hinge on our beam right here, let's talk about what is that we are seeing here. So here on this little window, we can see the force deformation pattern that this hinge will consider. And where this is coming from is a very common force displacement pattern for hinges on reinforced concrete structures that has been adopted in many codes. And I'll show you in the FEMA 356 code, which is a seismic rehabilitation pre-standard. And here I am in the page 215. And right here you can see exactly the same as the one in SAP2000. So it starts from the origin and goes linear until the hinge yields at point B. And then C, it's the maximum capacity of this hinge. After C, the hinge is considered to have failed, and it unloads to point D, where it has a residual capacity and some displacement until point E, where it fails completely, going to 0. So this is the same as we see here on SAP2000. We have from point A to B, B to C, C to D, and then D to E, and after E it goes to 0, as you can see selected here. These points here, IO, LS, and CP, they represent what we call performance limits. This performance limit here indicates the damage level that this hinge has suffered. So for example, if the hinge is loaded up to here, it still falls inside the immediate occupancy state, and the building where it is being included can be immediately occupied right after the loading. The same applies for the life safety, where it's the risk to the structure integrity starts to degrade, and the collapse prevention is where the building is almost at the collapse state. So this IOLSCP can also be seen here at the bottom of this window, where we can specify where we are going to consider this performance limits on our hinge force displacement diagram. If we want to see, we can click here and we can see exactly which one they are. And you can also see that they are color coded. Every point in this force displacement diagram is color coded. And when we include the shear hinges and analyze the results, the hinges will change color to indicate where in this curve they are. One last thing we're gonna do is that we will change the type of the shear hinge from force displacement to stress strain. When we change that, SAP let us change the hinge length. So here we will be able to put our hinge length as 1.5 times the effective depth, which is 685.5. So okay, let's click OK and start to implement the shear hinges on our beams. So we have this one selected. Let's select both of them now because we have the same shear hinges on both of them. Click on Assign Frame Hinges. And right now we're gonna select the shear hinge. So to calculate the relative distance, we're gonna do D divided by the length of this element. So this will give us 0.267. Let's add that. And the other one will be D from the end of the element. So we just need to do 1 minus this number, which is 0.3. Let's add again, click OK, and we should see 2 shear hinges on each element. So now that we have everything set up, we can start loading our beam. So before we go into the loading part of our beam, let's select all of our elements, come to Assign Frame, come to Hinge Overrides, and select this Auto Subdivide Line Objects at Hinges. Leave the default number and click OK. So what this will do, let's go back to FEMA, is that this override will allow the shear hinge to have a sharp descending line once it reaches point C. If we don't override the hinges, between C and E, it will do a linear interpolation where the load here, instead of going straight down, it will go linearly to point E. So now that we have everything set up here, let's talk about the load that we will input on this beam. So we don't know where this beam will fail, so we don't know which load we should apply here. So before we do anything in SAP, we should have an idea of how much load this beam can take. So for that, one easy, fast way to do that, to have a sense of how much this beam will be able to sustain, is to do hand calculations, use the coding provisions, for example. I already did that, and I figured out that by the ACI code, this beam should resist about 430 kilonewtons, and at failure it should displace about 25 millimeters. So since I calculated that it should resist about 430 kilonewtons, I'm gonna apply 2 times this load to this beam, because that way I'm absolutely sure this beam should fail. If it doesn't fail with that load, there's something wrong. Doing hand calculations is also a good idea because it will give you a sense if your model is wrong or right. If I calculated 430 and I get 1,000 capacity from this beam, there's something wrong. The same way, if I get 100 kilonewtons, I know there's something wrong in this beam. So to apply the load here, I'm gonna come to Assign and then Joint Loads. And I already created the load pattern force, and I'm gonna apply in the Z direction minus 430 times 2, 860 kilonewtons, and you can see the load here. For the type of loading that we are gonna use, just to exemplify in this video, I'm gonna do both a force-based analysis and a displacement-based analysis. So in a force-based analysis, what we do is that we keep increasing the load on this beam until it cannot resist any more load and fails. And in a displacement-based analysis, instead of the load, we apply the displacement on the beam and check how much force it comes out from the displacement we imposed on the beam. Since we only have one force in our problem, they shouldn't yield different results in terms of capacity of this beam. So one advantage of the displacement-based analysis is that because we are applying displacement and calculating the force that that displacement causes on the beam, once the beam fails, we can still capture the post-failure behavior of the element. In a force-based analysis, we can't, because like I said, we keep increasing the force and calculating the displacement of the element. Since it can no longer take any more force, once we reach the peak of our element, our force-based analysis can't calculate the post-peak response of the element. So you might think, then let's always use the displacement base because we want to see the full response of the element. But when we have more than one point load, for example, and they are not equal, we can't use displacement base. And to illustrate that, I have this example of a frame that was previously loaded. So this frame was loaded with 3-point loads, one in each story. If I wanted to apply a displacement load, I wouldn't know how much this floor would displace in relation to this floor and in relation to this floor. So I wouldn't know the values of the displacements to apply here. In that case, we had to use the force-based analysis because the displacement base wouldn't be possible. In our case, we only have 1-point load, so it doesn't really matter. And except for the post-peak response, our response shouldn't vary much between the two analysis procedures. So I already went ahead and created the force load pattern like I said before. And here in the load cases, I created both a force and displacement load case. So let's go into the force, and here to do a pushover analysis we have to change the analysis type from linear to nonlinear and keep the load case type as static. The load applied will be the load pattern force, which we just created, and right here at the bottom we need to change some parameters here. So the first one is the load application. Let's click on modify and show, and here we can see that we have two options, full load and displacement control. The displacement control will be used on the displacement load case. So here we're going to use the full load, and the monitor displacement will be at joint 2, which is the middle, and degree of freedom 3, which is Z, and in our case is the vertical. Here at the result saved, we're going to change from final state only to multiple states. So we're going to save and we'll be able to see the response in multiple stages and not only at when the load is totally applied. By putting the minimum and the maximum number of saved states to the same, we can be sure that SAP will subdivide our load in this number of states, and each state will be this load divided by 50 in our case applied to this beam, and we will have a monotonically increased load on this beam. So click OK. I'll show the displacement just so you can see it's exactly the same. The difference is that here we select the displacement control, we use the monitor displacement, the degree of freedom and the joint is the same, and here is where we input the maximum displacement we want this load case to impose in our node 2 at the degree of freedom of Z. So since I calculated 25 millimeters using hand calculation, I input twice that number here so I know this will fail. So click OK, click OK. And now we are ready to run our analysis. So first let's come to Analyze Set Analysis option and click on the XZ plane. Hit OK. And run both of our analysis. I'm not going to run the dead load here because it won't add up much to our beam. Our external force is definitely the critical load situation. So I'll click Run now. So here on the top left side we can see that we are looking at the force-based analysis and we are on step 0. So if we go here to the bottom and click on these arrows, we start to navigate through the steps, meaning that our load is increasing on this beam. So let's click a little bit here until we can see our hinges. So right here is where our hinges start to change color, and these colors match the colors of the force displacement diagram that I showed when we were creating the hinges. So here we are at the first column, which is the blue. And we see that at the next step, it turns into red, which means that this hinge has failed. So we can see that at the force-based analysis, these hinges fail pretty early on the analysis and pretty suddenly. And we also see that all the hinges fails together, even though these hinges close to the center, as I mentioned before, have both high shear and high moment, and these close to the supports have only high shear. The reason for that is that SAP2000 do not consider the coupled effects of shear and moment. So as far as SAP2000 knows, this hinge and this hinge have the same shear force on them, and the moment on this section here doesn't change anything for this shear hinge. So if we go to the displacement based, we are also on the step 14 where we left off from the force, and we can still increase that, and we can see that now the shear hinges change colors. They don't go directly to the red. It changes colors until it goes to the fail right here. So if we want to get the plot force displacement response, we can come here to the display, show plot functions. I already set them up here, but I'll show how to do it. Go here to the define plot functions. Change from joint displacements to joint forces, add the plot function, and here you can select if you want to know the displacement, the velocity, acceleration, the reaction, of which node you want to get this information from, and at which degree of freedom you want them. So I already did this here. So in joint 1 and 3, I am getting the reactions at the supports, and joint 2, I'm getting the displacement. So at the horizontal line of my plot, I want to have the displacement, and the vertical, I want to have the reactions. So I can show you the force and click on display, and SAP2000 will show you force displacement curve he got for the force analysis. I can change that to displacement, and here you can see displacement analysis, force displacement response. And you can also see that it looks a lot like the hinges force displacement diagram that we inputted on our shear hinges. And the reason for that is because since this being failed on shear, the force displacement basically followed the shear capacity until it fails. If you want to get that on a file, a text file, we can save it and export it and then go back to Excel, for example, and compare them. So I'm going to do that and come back with the Excel file. Alright, so here I am in Excel, and I set up this graph so we can plot the load versus deflection at the midspan of our beam. These two lines right here represents the hand calculated load capacity that we got using the ACI code, and also the deflection. So I'm gonna show the displacement and the force based analysis that we got. The yellow one is the force based analysis, and the gray one is the displacement based analysis. What we can see here is that the gray one, once it reaches the peak force, it unloads to a residual force and then it goes to zero. Whereas the force-based analysis doesn't, and it goes indefinitely once the peak is reached. As we can see, the load capacity calculated by SAP2000 is about half the one we got by the code. A very high conservative response by SAP2000. Since this is a shear controlled beam and it fails with shear, the shear hinge is the main problem and the main factor which results in this high conservative response. So we can conclude that the shear hinge that the SAP2000 calculate by default, it's not very suitable for shear critical beams, and we should modify it, which we won't do it in this video. I'll change the chart type to show the point loads that each one calculated. So here we can see that the displacement base calculated a response even after the beam started to yield. Whereas for the force-based analysis, once it starts to yield, we can see that the calculated points are very spread apart. This indicates that the analysis has reached its peak and the corresponding results are not meaningful anymore, as the analysis is trying to increase the load but the beam cannot sustain it anymore. So we need to cut the load displacement response when the spreading starts to become too large. In this case, we can already see a large spread from this point to this point, which indicates that the beam has already failed by this point. So we can either cut the force-based analysis in this point to indicate that it fails, or even cut at this point right here, which would indicate the peak capacity of the beam based on the force-based analysis. Normally we don't have the experimental response, but in this case we do, and I'll show you how did this beam behaved when it was experimentally tested. So we see that it goes a little bit above the one we calculated with the code, and considering the code conservatism, that's okay. But we can also see that the stiffness of our beam is not quite correct to the experiment. And one of the reasons for that is that SAP2000 does not calculate the cracking on the reinforced concrete. That's why we have this off stiffness response. One thing we can do is that we can use the ACI code factors to account for the cracking condition of the reinforced concrete. So here I am at the ACI code at the clause 10.10.4.1, page 149. This is ACI 318M11. And it says that it shall be permitted to use the following properties for the members in the structures, and for our beams to use 0.35 the gross moment of inertia to consider for the cracking. And the way we do that in SAP is that we come to the section that we defined, concrete section, we modify it, and here in the property modifiers we set the moment of inertia to 0.35 in the axis that we are doing our loading. In my case, I just put the same for all the axes. And when we do that, I'm gonna show you, we get this response, which is softer than the previous response we got and follows the experimental response a little bit closer than the previous response. To illustrate how the confinement properties that we model in this beam do not change anything in the response, I also did an analysis where I removed the confinement properties completely, and I just left the concrete and the longitudinal reinforcements on my section, and I'll show you the response right here. And as you can see, you can't actually differentiate the two responses, the one where I considered the confinement and the one where I didn't consider the confinement. The reason for that is, like I said before, that confinement properties that change the stress strain response of the concrete only affects the fiber hinges, which is the moment axial hinge. And since this beam was mainly governed by the shear hinge, the difference that the confinement caused in the moment properties of the hinge doesn't change anything in the shear resistance of the beam. So to try to fix all these problems we have with very conservative shear default shear hinge calculations, and our shear hinge not consider anything of our stirrups layout, we can do custom shear hinges where we will go into the shear hinge window that I showed before, and we will edit those points that the force displacement of the shear hinge curve follows. We will do that in future video and not on this one, but this is something we can do to get a better response on shear critical elements. Another thing we can see is that by using elastic elements with nonlinear hinges, such as the SAP2000 model we have here, give us very rudimentary response. Like we can see, it's basically just a constant stiffness up to yielding, and then a constant stiffness up to peak, and then it fails. A fiber-based frame element, which can consider distributed plasticity along the element, would give us a much better result and a much closer fit to the experimental response than the model we have in SAP2000. To illustrate that, I have the same beam model in vector 5, and you can see that the response in vector 5 gives a capacity closer to the one we got in the experimental result. And we can also see nuances on the analysis, such as cracking of concrete, peak capacity, post-peak response, with much more details than the SAP2000 analysis right here. In addition, such elements can also give you visual insights such as cracking patterns as the beam gets loaded. Here I just have the half of the beam. The load is coming right here. And we can see that cracking pattern as the beam gets loaded, and we can get a sense on where we have the highest effects on the beam until it fails. So features like this are present in distributed plasticity frame elements such as the one in Vector 5, but is not present in SAP2000, which we can only see that the beam failed by checking the color of the hinges. We don't have any cracking pattern or any visible yielding of reinforcement, nothing. We only have the hinges colors to give us a sense of what kind of failure we have in this beam. So to finalize, a good prediction of a element response would give us about 20% more or less the one we calculated using the one we obtained using the experiment. And we can see the SAP2000 here is almost half the response we got experimentally, which will give us an experimental to numerical ratio of about 2, which is not good. So SAP2000 analysis in this case is not good for the prediction of the capacity of this beam over here. So with all that in mind, let's go back to our handout and try to answer those questions right here. So first one, estimate the cracking load. As we can see from our plot, we don't know when the cracking load happens because from the start of the loading condition to when the hinge yields, there's no difference in stiffness. In Vector 5, for example, we can notice a kink on the force deflection response where it indicates that the beam started to crack. But in SAP2000, we don't have this information, so we can't answer that. The ultimate load by SAP2000 would be about 260 kilonewtons. The midspan deflection at failure, judging by the displacement base, would be about 24 millimeters. And the crack pattern, again SAP2000 doesn't give this to you. And the failure mode, we know it's shear failure because our shear hinges are the one who failed, but we don't know where the failure happened because all of our shear hinges fail at the same time.